Good evening, everyone. Please, anyone confirm, am I audible properly?
Yes, sir.
Okay, thank you. So, welcome to the session, and this session is all about the week two programming session. We will try to do the programming assignment that we already have on the portal, and try to demonstrate the kernel PCA using that. Okay, and other than that, we will be having this as an open session where you can ask your doubts regarding the week two concepts and whatever questions whatever doubts you have in the assignments, right? Okay, so I hope all of you have gone through the week two content and have solved the assignments as well. So, if you have any doubts, you please ask your doubts, and then we'll go for the programming part of that. Or should we start with programming part and then in the last we should do the open session? How do you want me to do that?
Sir, before you start, I want to ask about this kernel PCA. Basically, I've gone through the lecture, but
Hmm?
I've not understand it. Can you please elaborate it? What is it and how it is solving our problem?
So, Asutosh, have you attended the previous session on the summary part?
Yes, sir, but at that time I was not watched the lecture. I just watched it before yesterday.
Okay. So if you want me to explain everything, it doesn't make any sense because we already have session on that, and you can always go to the YouTube. It is already recorded, and you can see whatever we have done on that session. But if you have particular doubt in particular concept, then I'll take that. Otherwise, it's not a good idea to come repeat everything once again.
No, sir, not repeating everything, but can you just briefly go through it? Just to
Briefly
start
through what?
through the kernel PCA.
Okay, so what did you gain? Whatever you have understood, please explain. Then I will try to correct you. Or let me open my whiteboard and then start. Give me 1 minute. Okay, if the YouTube link is not updated in the calendar, please go to the live session sheet that is already shared with you all. If you go to the live sessions folder in the supplementary content, where you will find a sheet there. From there, you can access all the link to the live sessions. Okay, so I think I should start with the programming part because my whiteboard is not working right now. So let me check once more. Okay, so let me share my screen first, then we'll take your doubts there. Can you see the whiteboard here?
Yes, sir.
Okay, fine. Okay, so you want me to explain the kernel PCA, right? So what is our target? Why we need kernel PCA? Why we cannot stick to the PCA algorithm? What is our target by kernel PCA?
The learner, sorry, the linear, like a non for
Sorry.
non-linear representation, we were not getting any conclusion about the PCAs. That's why.
Okay, then what we do? If the data set is not linearly distributed, it means that there's no, I mean, the data set lives in nonlinear subspace of any higher dimension in that particular dimensional space. So what we try to do there, we project our data set into higher dimension such that it comes into the linear subspace. Once it comes into the linear subspace, we apply the PCA algorithm because PCA demands the data set to be linear, to live in a linear subspace, right? So that is our target. We try to project our data set into higher dimension such that it comes into the linear subspace. That is all our motive using kernel PCA. So what we do, we try to find some transformation such that whenever we apply that transformation mapping to our data set, the data set comes into the higher dimension, and in that higher dimensions, that data set comes into the linear relationship, right? So we need to find that transformation. Once we have that transformation phi, we are done, right? Because that's all we need right now. That's where the problem comes in the PC algorithm. And once we resolve that problem, we can easily apply our PC algorithm there. So that is all we need right now. All other things we have already cooked up, right? So okay, so that idea is clear, right?
Yes, till this point, everything is clear.
Okay, then okay, so my tripod is somehow not working. I'm not sure why. Got stuck at some point. Yeah, I think it started now. So that's all we know. That's all we need, right? So let's say we have data set x1 up to x1, x2 up to xn, right? And we try to find out such one transformation phi such that those transform data set x phi x1 to phi xn, these are my transformed data set now, and this phi makes sure that these all data points are lives in a linear subspace. Okay, that's all we need. So there's a clever way to skip this all the calculations, because once we need once we have this file, we have to apply PC over over those data points, and we have to find the K matrix, right? Remember the PC algorithm where we need to find the K algorithm, which is of shape which is x transpose x. In this case, our data set become pi x, so this will become pi x transpose pi x. All we need to calculate this pi, then we have to calculate their eigenvalues, let's call them lambda 1 to lambda and whatever those are, right? And corresponding unit vectors. Okay, so uh, just stop me wherever you have the doubt or you didn't understand the concept. Okay, so these are my eigen values of this K matrix, and we find the corresponding unit eigen vectors as well. Let's call them alpha 1 to alpha n. Okay, and what we do next, and we call, you remember in this algorithm, we actually try to find these w k's as the linear combination of the data points, right? This alpha k, right? So these alpha k are actually, okay, so let's call them betas, not alphas. So this become beta 1 to beta n. So these are the unit eigenvectors corresponding to these eigenvalues, right? So remember, these are the unit norm eigenvectors. Okay, so what we do, these alpha k are nothing but whatever these coefficients are. So these alpha k are nothing but these beta k, the kth eigenvector, divided by the eigenvalue root k. So once we have this alpha k, we are done, because now we have this eigen principal component, kth principal component, that becomes the linear combination of these data points, right? Till this point, do you have any doubt? This I just explained the algorithm. If I haven't, I just skipped this part, how to find this phi and how to come up with this data point, right? Once we have these data points, I'm just explaining the algorithm that we have already seen in the first section of the week two, right?
May I ask a question which is a little
Yeah,
more
yes, sure.
fundamental than this?
Yes, sure.
When you say 5x1,
Hmm.
phi, is it a function? Because I went through the video of the last section. I mean, when you taught the class on Thursday, unfortunately, I'm a working professional, so I could not make it. I saw the video.
Hmm.
When you say you give a specific example of x1 square plus x2, sorry, x1 square, x2 square plus 1.
Hmm. Hmm. Hmm.
And for that, you would derive 5x1. So I was not really clear what exactly is the function there. Would you be able to
No, no, no.
just
So
show?
this is a transformation mapping.
Okay.
For assume your data points are lying these xi's are lying into two-dimensional space. For
Mm-hmm,
simplicity, assume they are lying into two-dimensional space.
mm-hmm, mm-hmm,
Let's say you have n data points, right?
mm-hmm.
Or say n equal to 10. 10 data points you have. So x1 is some point 2 comma 3, or I equal to some 4 comma 6, right? So they all 10 data points are lying into two-dimensional space.
Mm-hmm.
Now, so all we know that they don't have linear relationship within the features. I mean that x some those relationship between feature f1 or f2, they are not linear. So what we cannot apply PC here.
Wait a minute, please. F1 refers to the first element of vector
F1
x1.
is first feature or say first input,
Okay, okay.
and this is the
F1 is not
second,
related to F2. Okay, not
right?
necessarily. Okay. Mm-hmm, mm-hmm.
Yeah. So some nonlinear relationship they have. Let's assume they have some relationship kind of f1 square plus f2 square equal to 5, something like that.
Okay,
Okay. I didn't take those points according to this relationship, but assume those data points follow
sure,
some this
sure.
relationship, right?
And from here, you
Now,
move into six-dimensional subspace. F1
now
square.
what our target is?
Mhm.
We have to come. We want those features, those this relationship to be linear one. Because if
Correct,
we want to apply PCA, we have to make sure that they live in some linear subspace of any dimensional space, some higher dimensional space, right?
correct, correct.
Now, what I will do, I just, if my initial initial input stage were F1, F2, right? Two feature
Mhm.
F1, F2.
Yes.
What I want some transformation mapping
Mhm.
such that in the higher dimensional space, it becomes linear. Okay, so what I
Right.
will do, I will just transform this into F1 square, F2 square, some F1, F2 or F1, F2 or constant, right?
Yes, yes.
So in
Uh,
this space, this becomes six-dimensional space. Now in this space, my features are what? Now my features are f1 square, f2 square, f1, f2, f1, f1, sorry, f1, f2, f1 constant, right? So these are my six
correct,
features. In
correct.
this space, if you look at this relationship, can you call this relationship a linear one into this input space?
Yeah, it's a linear one.
Because this one is now my one feature, this is my
Coefficients. Yeah,
another feature, and
yeah,
if you take this as a one feature, this as a second feature, they have
yeah.
some linear relationship, right?
Right.
So this mapping I'm talking about here, whatever I just mentioned here,
Yeah,
this phi, this is one mapping, right?
yeah.
Okay, so there's one clever way to skip all these calculations of transforming each and every data points to higher dimensional.
Can I
There's,
interrupt here once? Can I interrupt here once?
yeah, yes,
So
sure.
far, it was very clear how we
Hmm.
are transforming. When you say phi of x1,
Hmm.
it is only one variable you are taking, so that is where I am a little stuck.
Yeah. So let me do for some points. Let's assume you have one point x1, which is something like uh, so let's say it's following this relationship, right?
Mhm.
Let's say f1 is equal to 1, then it will become 2, right? 1 comma 2. So this is one data point, and
Okay.
you have some phi which is coming from this relationship, and now your data point becomes six-dimensional, right? So you
Yeah.
have six-dimensional. So your first feature is f1 square, right? And this one
Yes.
your f1, and this is your f2. For this
Correct.
particular point I'm talking about.
Correct.
Okay, so this will become your phi x1. Okay, so
Phi of
now you have
x1 is
six
that.
values here
Okay.
because it is coming from six-dimensional space. So what
Okay.
will be the first value here? F1
It's
square,
will
that is 1.
yeah. It will be
Second will
one.
be
It will
f2
be
square,
two, and
4,
rest of them
f2
will be
square.
zero anyway. Oh, four. Okay.
This is f2 square.
Oh, okay. Okay.
And
Okay.
here it it is F1, F2. This is become 2. This
2,
become 1. This become
1 and 2.
2 and 1.
Okay.
So
Okay.
now this point
Thank you.
has transformed to this point.
Okay. Got it.
And every n point is transformed using this relationship, this fly.
Okay.
My data points are these, and I will apply my PC over this,
Okay.
over
Got
those
it.
data points, right?
Okay. Okay.
Okay.
So,
But that's all I'm saying. We
Mhm.
need not to do this transformation at all. We even don't need phi at all, right?
Mhm.
There's there's very there's one function that we define that we call as kernel function, and that takes care of
Phi of
everything.
phi transpose x
Yeah.
into
So
phi of
remember, when you
x1.
will apply the your PC over these data points, let's call them now. This call 5x1, and similarly you will have n data points, right? In the
Mhm.
6-dimensional space, 5x2
Mhm.
up to 5xn,
Mhm.
right? So now you will apply PC over those points, right?
Mhm.
Once you will apply, what will be your next step?
Next step will be when I'm applying my PCA, I need to find the vector direction in which the variance is maximum.
Yeah. So how you will do that?
Covariance matrix.
So there's one way when you will apply the covariance matrix, which is x transpose, or in this case it will become phi x transpose, right?
Correct.
Then you will find the eigenvalues, eigenvector, and those eigenvectors become your principal components. But there is another way that we did in the first part of week 2. We
Mhm.
find the K matrix, right?
Yeah.
So what is
You
K
find that
matrix?
kernel, and you said it is phi t
So it is
x1,
phi
phi
x
t.
transpose phi x, right?
Yeah. Yeah. Yeah.
Yeah. So you have to calculate this matrix once you have these data points, right?
Mhm.
So kernel methods actually,
So
for
this
kernel
has
methods,
uh,
we don't even need this phi. We don't need to transform every data points and then phi k. So what kernel function is? Kernel is a function from some d into d, rd into rd. So it takes two data points and do some operation over those data points, and then give the output r, right, in real number. So actually, if you transform the kernel function into two data points, let's call them x1, x2. These are two arbitrary data points, and this function, actually, whatever the function is, its actually value should be equal to this value, phi x1 into phi x2. So
okay.
this is the property of kernel function, and that's what we need, right? This value we need to find
And
the k matrix, right? Because the
yeah.
for ith point, the value for k matrix will be phi x I transpose phi xj, right? So,
So
so for any phi, if we have kernel function, then we are done, because the kernel function makes sure that this value will give this value I can calculate using this function. I don't even need phi. For
true, but
example,
the assumption here is that the kernel function will be applicable to all the points.
all the points.
Okay, that's an
Okay.
assumption,
So
but it may
yeah.
not always be here,
No,
right?
no, that's how we define a kernel function.
Okay.
Okay. For assume, let's you are doing polynomial transformation of degree 2. It means that you have initially features, let's call them two features, f1, f2, two-dimensional data points, and you are applying 2-degree polynomial transformation over those. So your data points will come into f1 square, f2 square, f1, f2, f1, f2,
To all the
and constant,
constant.
right?
Yeah.
So these are your polynomial transformation, some phi. Okay. So
Mm.
corresponding to this transformation, we have a kernel function which actually is defined as x1 transpose x2
Mhm.
plus 1 raised to power 2. For any d-degree polynomial, this is 2-degree polynomial transformation. For any d-degree polynomial, the kernel function is defined in that way. Okay, so you need not to do any this transformation and then apply phi x transpose phi x for every data point. You just put those data points here and get the value of ijth element for the k matrix.
Sir, one doubt here. Maybe it's silly, but the kernel function is returning a real number value, right?
Yeah, real number value, because if you look at the definition of the kernel function, it is defined as phi x I transpose phi xj, right? So this is a dot product which is a real number.
Okay.
Mm. Okay.
One question. What is x1, x2? It's just
These
the
are
same
data
x,
points.
right?
These are data points. for let's take two data points,
If you
1
could
comma
just
2.
move up.
X is a matrix or it's a vector?
X1 is a data point here.
Data point being a vector, column vector, correct?
Yeah, column vector. Yeah, of course.
Right. The initial data.
Okay.
Okay.
So suppose for
Here, when you
four
could you
feature,
please go
Yeah,
up a
please
bit?
one by one. Yeah.
yeah. So for 4 feature and 2 dimension,
Hmm.
what will be the X1 and what will be the X2?
For 4-dimensional data points, you mean?
A 2 dimensional data point
Hmm.
with 4 data point with 2 dimension.
4 data points you have. So n equal to 4,
Yeah,
right? So
yeah.
so assume
And
you have one data point 1 comma 2. Another is
okay,
4
got
comma
it.
6. Okay, so
Okay,
this is your
thank
X1, this is your X2, and you just apply the X1 transpose X2, right?
okay. So it's a pairwise basically.
Pairwise dot product, yeah,
Okay, okay.
and
Thank
yeah,
So this kernel function is a standard one, or it varies
yeah.
according to?
For different files, you have different kernel functions,
Okay, it's not
right?
a standard.
So for standard transformation like polynomial transformation, we have a kernel function, right?
Okay, yeah.
For Gaussian RBF kernel, we have, okay. One is
Okay,
very standard one is RBF kernel,
okay. But
which
at
is
least for
generally also
polynomial,
called
this is
Gaussian.
fixed. At least for the polynomial function, this is the standard one.
Yeah, this
Kernel
is the standard one. This is called x1 transpose x2 plus
plus
1 raised to power d, the degree.
p.
So it's
Yeah.
constant. I mean, it's a standard one, like
Yeah, this is
x1,
this.
x2. Will,
This is the
okay.
standard. For any input space, let's call this RD space. So D don't, let's call it P power P, because not to confuse
Okay.
between P and D. So this is D-dimensional space data point, and we are doing P degree polynomial transformation.
Okay. So x1 transpose x2 plus 1 power
P.
the power p, but p is, do we know p already,
Yeah, yeah.
or
That
is
that that we if we are doing 2-degree polynomial transformation, then P becomes 2, right?
okay, okay, okay.
Sir, can you repeat it again? What you said?
Sir, same thing, same line, sir. The X1, X2, they are the feature or data points, sir. I mean, when we say data points like 1, comma 2, okay, this is the one data point, or like, or is it a feature like, okay, 1 and 2?
So whenever I write x1, x2, I mean, but why don't I mean the data points? Okay.
Okay,
So whenever I
so
write as x1 as
okay,
2 comma 4, then this is the first feature value. This is the second feature value.
yeah. So, sir, I mean, so when we say X1 transpose X2, when we say, so
Mhm.
does it mean like this particular system has only two data points in this system?
No, no, no. These are some general data points. I just mean
Yeah,
it's not
yeah.
one data point, second by data point. I mean you have to do if so cave matrix you will do n by n matrix, right?
Huh.
And n by n matrix. So at ijth entry, the value will be kxi xj. So you will do xi transpose xj plus 1 raised to power 2, right? For the first entry, very first entry will be x1 transpose x1 plus 1 raised to power 2. So it will become 2 comma 4, 2 comma 4 plus 1 raised to power 2. So this is a simple dot product, right?
Yes, sir. This is be fine. Okay, what about the next point, sir? This is what I understood. Okay, fine. For one
Hmm.
point, and with using two data
Yeah.
points, I can find
So
the.
let's say you have second data point as 4 comma 6.
Okay,
Okay, so here I did some mistake. It
2
should
4
be
2 comma 4 and
2
2
comma
4.
4. So I'm taking x1 transpose, yeah, x1 transpose x1. So 2 comma 4, 2 comma 4, because this should be a constant number raised to power
Correct.
2, right? So this is your second data point now. So the second entry in the K matrix should be what? It should be phi x1 transpose phi x2, right? And this is equivalent to K x1 x2, right?
sir. Yeah.
Yeah.
So let's yeah. So it's not X1 transpose X2. It's actually X1 transpose X1 only, right? You can say. Can we say like that?
Um, mm,
Sorry,
Hari, I
sorry, could
think what
One point is 2, 4. Yeah.
you?
Hari,
Yes, please.
it's only if it is x1 x1, then you have x1 and x1. If it is x1 x2, then it is x1 and x2. So if you have two data points like written over there, 2 4 and 4 6, first you have 2 4 transpose 2 4 plus 1 power 2, And the second one is going to be second as in to fill up the matrix, x1, x2 will come, right? First it is x1, x1, next it is x1, x2. For x1, x2, it is going to be 2, 4.
Okay.
2,
Okay.
4, and so it will become 2, 4,
2, 4
and the second
transpose,
data
and then 4, 6. 4, 6 plus 1 power 2. And the
plus 6.
third element is going to be 4, 6, 2, 4, because it is x2, x1 now. Matrix is 1, 1, 1, 1, 1, 1, 2, 2, 1, 2, 2, right?
Yes, so
So the
K
four
matrix become n cross n
It's a 2 by
matrix,
2
where is
matrix.
n is the number data point.
It's a 2 by 2 matrix, right? No, it's
yeah,
a
it's a
2 by
2
2
by 2.
matrix.
It's a
Okay.
2 by 2
So
of 2 by
1, 1,
2s,
2,
which
2, 1, 2, 2. Okay.
yeah.
Okay. That makes
So
sense,
first,
sir. So this
So,
is this actually, sir, if you write this symbol right, it's very helpful to understand the video, sir. Mostly we get confused in okay, what is x1, x2, and what are the features? Like I mean, we get confused while interpreting that video. Yeah, it's very much clear sir, right now.
Sir, if I can just take you back to the beginning of your whiteboard, please.
yes, sure. So that idea is clear, right? What's actually happening. So I see the confusion here. Some of you are got confused within the x1 and feature, what feature value in x1 and something like that. So it's your responsibility. If you got confused within something, you just put some numbers for features and do some calculation, manual calculations, right? But in practice, it's not possible to do such calculation at all. Yeah. So where you want me to do?
I've understood almost all of what you've said subsequently, but there's just some fundamental things that I'm not got. So we're saying, supposing the data points are in, say, R2 with two features. That is what you had given an example of,
Yeah.
F1 and F2.
Hmm.
Now, you've said here F1 squared plus F2 squared is equal to 5. What is this particular thing?
Okay. So yeah. So where we started with, we started with that. We know we want to apply PCA over some data points, right? And PCA demands our data points to be linear, have some
Right.
linear relationship. Let's
Right.
assume this is my first feature F1, this is my second feature F2, right? And my data points has some relation, something like that. It is distributed something like that.
Yes.
Now I can see that this relationship between F1 and F2 is not linear at all, right? So
Right.
this is following some F1 square, F2 square equal to some constant 4, right?
Right.
Right. So we want these data points to project into some higher dimension. I cannot draw a higher dimension here. 6-dimensional space such that these data points come into linear form, linear subspace.
Right.
Right. So that's why we are doing some transformation for the feature F1, F2, and we will bring into the another space that is some 6-dimensional space using 2
How
degree.
do I decide it is 6-dimensional?
Yeah. So for this particular example where I've done the 2-degree polynomial transformation, I can easily find because initial feature was my F1, F2, right? F1, F2. So initial
Yes.
feature by F1, F2, and I'm doing what transformation? Phi is now my 2-degree polynomial transformation.
Okay.
Okay. So polynomial, what it does, it just takes the powers, right? So F1 square, F2 square is 2 features. At max power should be 2, right? So F1, it is again less than 2, F1, F2, right?
Okay.
In constant terms. So now I can easily say that this becomes my 6-dimensional space.
So when
Or
I'm
take
taking
one more
a
example.
2-degree polynomial, I would have 6 dimensions. Yeah. And
So
if I
one
take
more example
3-degree,
just to make things clear.
sure.
Let's assume you have 3 features F1. Let's assume you have 4 features F1, F2. I cannot do manually, but I just give you the idea what actually happening. You have 4-dimensional space now, R4. Okay, and you are applying 2-degree transformation,
Yes.
polynomial transformation.
Yes.
Okay. Now, what do you think will be the features here in the feature space?
F1 squared, F2
Yes,
squared, F3
similarly,
squared,
F4
F4
square and F1, F2,
two,
F1,
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 F3, F1,
something
F4.
like that. What if I do 3-degree, let's assume 4-degree polynomial transformation?
Oh, that will be very high.
Yeah.
Maybe, of course, F1 to
F1
power
raised
4,
to 4 and F2 raised to power 4 and all up to constant term, right? F1 cube. So manually you cannot find what will be the dimension of the higher space,
Is it
right?
part of permutation combination?
Yeah, part of permutation combination. From there you can just remember one formula here. If you have d-dimensional space, d-dimensional data points, d data points, right? So your input space is d-dimensional. Now you are applying p degree polynomial.
Okay.
Okay, so this only follows for polynomial transformation, right? Okay, don't be confused within different transformation. So
Okay.
for 2-degree polynomial for transformation, you're doing over d-dimensional data points. Now your input, the transform space will be d plus p c d space, dimensional space.
So if we took two features and made it into a 3-degree polynomial, we would have 2 plus 3, 5, C 2.
2, yeah. Okay,
That
so
many,
D is the input space, the dimension of the input space. P is
yes.
the degree for which you are doing polynomial transformation.
How do we decide which degree to take? 2-degree, 3-degree, 4
Okay,
degree?
so if you know the relationship within the feature, then you can say that okay. So for this example where I took the relationship f1 square f2 f1 square plus f2 square, so I can say that if I do 2-degree transformation, then probably this relationship comes into the linear relationship, right? But if you have more than two features, you cannot visualize your data points. Then you have to tune your degree as well, right? Tuning, you will come across this terminology later, but tune means you choose different values of degree and check which one suits better for my data set.
I mean, that's fine. Like, now I've done a transformation from this d-dimensional to a polynomial of 2-degree. How do I know that 2-degree dimension polynomial is actually suiting my data?
Okay, so this particular example, I have the relation. I know the relationship. My relationship were f1 square f2 square, right?
Yes.
Equal to 5. Now my input, now my transform space has the features f1 square f2 square f1 f2 f1 and f2 and constant, right? So this is my one feature here in this transform space. This is my second feature.
Yes.
So isn't it a linear relationship? Because let's call it h1, let's call it h2
It is
equal
equal
to
to
5,
5.
right? Because this is my one feature. This is my one feature. This is my second feature. So isn't this relationship linear?
Well, it is looking linear, yes.
Yeah, yeah. So I see the confusion. You are confused with the powers right here. But I am calling this f1 square itself is a one feature. This f2 square is my second feature.
Hmm.
Okay, so this relationship now is my linear relationship. But if I take only f1 as a feature or f2 as a feature, then it is a quadratic relationship.
Sorry, then it is a?
Quadratic one, I mean the second degree relationship,
Okay.
right?
So this transformation from these d dimensions to which is a non-linear relationship to a 2-degree polynomial is the phi.
Hmm.
The
Yeah.
transformation itself is phi, right?
Yes. Yes.
Okay. It's a very abstract at this moment. It's not...
Would you
So
can
what
you
would be
move to the
the
left
what
side?
would be the so if
Sorry,
we have to so if you have to work this out,
Hmm.
so how do we work it out? You're given the relationship as f1 plus f2 square is equal to 5, some kind of parabola.
The circle.
it's a circle
Okay.
actually.
Yeah,
Circle. Sorry, I see
parabola.
circle. Yeah, circle. Go ahead, sir. I'm just trying something. I'll figure it out.
Okay.
Can you move to the left, please, once? On the left side where you had put this d plus PCD polynomial and just move a little left.
Okay. So somehow my streak is that
Okay.
getting frozen. I don't know why it's happening.
Sir, in the meantime,
Hmm.
hello, just to reconfirm, when we say D dimension data, it means D features are there, right?
Yeah, D features are there. Yeah.
Okay, thank you. Just to reconfirm.
So, but what is in this example? What would be the kernel transformation? Like I'm looking for the what should be the adequate kernel transformation, or how are we coming
Okay.
to this polynomial transformation? So
Okay. So that's what.
how can I write this as what is the phi in this case? Can I?
Okay. So if I talk about this particular example that I took here, I just transform my initial input is one f1 f2, right?
Correct.
And I'm mapping this to this thing f1 square and this thing. I mean this thing, right? So this mapping
Correct.
is this mapping I'm referring to as a 2-degree 2-degree polynomial transformation, right? Because what is a mapping? What is a function? Mathematical function. It just takes one. It takes one input and map it to some other points, right? Some other input,
Correct.
right? So it takes two-dimensional point, this whatever the function is, and it takes it to the six-dimensional point. So that mapping I'm referring as a two-degree polynomial transformation mapping. 5. So it's just like you have one space and you are moving your data points one space to another space using some mapping 5. Linear
Sir,
transformation you must have done in linear algebra course linear transformation, right?
Yeah, correct. So no, I got it. The one question is that we say that the data points now will lie in a linear subspace, right? Of this, this is what is the rest of the kernel transformation and all is clear, but this one, when we say now, see, there is a now the transformed feature, right? We move from R2 to R6, right? Now this R2 lies in some linear subspace of R6. Now, what is that linear subspace? Is it R5?
No,
R4?
R2 is not lying into linear subspace.
No,
R2 was my initial input space.
Correct.
And I have taken my data points from R2 to R6. Now I will work out in the R6.
Correct. Now, when we say, it lies in the linear subspace of R6, in the lecture.
Okay. So so let me explain it using some lesser dimension. Let's assume somehow I transform my data point from R2 to R3.
Okay.
I don't know the actual transformation right now. So this thing is creating problem. So let's assume you have some phi transformation. I don't know what phi is. I transform my initial data points. Let's call them R2. So this is creating problem. Not so bad. R2 to R3. Okay. Now my transform space using some phi, I've transformed my 2-dimensional data points to 3-dimensional data points.
Correct.
And my transform space is 3-dimensional. It's some space, 3-dimensional space. Now my features become H1, H2, H3, something like that, right? And my linear subspace will be a plane in this.
Correct.
So my data point must be lying in this plane. All those
the transform data will lie in that plane.
In that plane. So this is my linear subspace of 3D. Okay.
Correct.
And
but what I'm asking
two-dimensional space. Sorry.
What I'm asking is the transform data is lying on that plane.
Yeah. So for 2-dimensional space, what is a linear subspace?
A line,
right? Because we line, and when we call data point to be linear, when they are coming from this line, right? They are following some linear relationship. Similarly, if in 3D, if they are lying on a plane, I mean they have some they are coming from a plane, they are lying in some plane, then we call them they live in a linear subspace of 3D. Okay. Similarly, for 6-dimensional space, there will be 5-dimensional hyperplane.
Sir, all these planes should pass through the origin, right?
No, need not to be, but we make them mean centered before applying the PCA.
Okay.
So
No, then if it's not centered, then I think there was a term which was used in linear algebra, like when we
affine subspaces is what you're referring to.
Yes, affine subspaces. Yeah. So these would be affine subspaces, right?
No.
If it's
if it is not passing through 0, yes.
Yeah. Okay. Thank you. That
right. So for 6-dimensional space, my hyperplane 5D hyperplane becomes linear subspace.
Why
it
would
has to be why that's my question. That's my question, sir.
You're removing the constant, is it?
Not removing constant. So you just because I cannot draw a hyperplane because it's 6-dimensional.
Okay.
You just take you just bring all the things into 1 dimension, 2 dimensions to make all the things clear. In 2-dimensional space, my linear subspace is a line, which is Bundy line, right? 1D
is equal to mx. Okay.
Right. Yeah. In the 2-dimensional space, or 3-dimensional space, my plane is 2-dimensional surface, right? This is 2D. Yeah. This is my plane.
That's my question, sir. If let's say it's R6, why can't the transform data lie in R4? Why should it be R5?
Okay, so that
means some of the variables perhaps are correlated, Vasu.
Yeah,
or
it
rather,
can be something like that. It may lie in R4, it may lie in R3. Not an issue. But generally, what happens? We tries to find such transformation only. Okay, be going from R2 to R6, and my space, and I call them to live in a linear space when they are coming from sub five dimensional hyperplane.
Okay.
Um, on the question on D plus PCD,
Mhm.
what I wanted to understand is what is the, I mean, that gives me the final dimensions of the transformed subspace, or what is D plus PCD representing?
So that is only for p degree polynomial transformation.
Okay, but it
Okay.
represents the final dimensions or
Final dimension of the space, transform input space. So this become D plus P, C D. This is the dimension of
okay. D
dimension of
plus P CD. Okay, I read it differently. That's the reason why I was scratching my head. Sorry.
dimension
I
of
thought it was
the
D plus
transform
PCD is
space.
what I was thinking. I did not realize this.
This is the size of
Sir,
basically transform matrix, right?
Yeah, in that course, if you find the covariance matrix in the in higher space, I mean the transform space, where now D becomes this one, right? Capital D becomes this.
Yeah,
So your
exactly.
covariance matrix becomes D cross D.
Yeah, yeah. Thank you.
sir,
Okay.
can
But
you just
we
move?
generally work out with K matrix, which is n cross n always.
Okay.
At the
Sir,
point.
can you just move up a little bit?
Sorry,
Uh,
you said K becomes n cross n matrix
K
always,
is
right?
always n cross n. N is number of data point.
Okay, okay. The covariance matrix is basically this one, D plus P.
Yeah, yeah. Because now we have come into the capital D dimensional space.
Okay.
Okay.
So no matter how whatever the degree of transformations we apply, the K will always be based on the data points, right?
Yeah, yeah. It's always gonna be n cross n matrix.
Okay, okay. Thank you.
sir, can you move just a little bit up no, to the 3D plane you were showing?
3D plane.
Yeah, the yes, sir. Here, I don't know if I'm getting it wrong or not, but the whole point of the transformation was to get a linear relation, right?
Hmm.
But after the transformation, you're saying that it could be a plane. The points could lie in a plane.
So in two-dimensional space, where all we have two features, the line is a linear subspace, linear relationship, right? But in the higher subspace, where we have three, let's say we have data points of 3 dimensions. This relate, what is this relationship? X1 plus X2 plus X3 equal to some constant called K. What is this relationship? Isn't this linear one?
Yes, sir. This is a linear one.
So what is this equation? This is a plane, right?
Okay, okay.
Okay. Similarly, for 5 dimensional space, some linear relationship will be f1 plus f2 plus some constant can be multiplied always plus c f3 plus something d f4 plus e f5 equal to 7, right?
Okay, so
So
clear, clear.
so this is a 5 dimensional hyperplane into 6 dimensional space, right? So this one is my linear relationship in 6 dimensional space.
Okay, so I was thinking that it would lie in a plane or something. So, in a line. Sorry.
No. It linear relationship actually comes from the which space you are in, and our tendency is to line just because we always work out in two-dimensional space. That's why we think linearity means just a line. In three-dimensional space, linearity means it's a plane. In higher dimensional space, just
Okay, okay, got it.
hyperplane, right? Linearity is not just a single line. It can be a plane into 3D or something like that. I hope that makes sense.
Yeah. Thank you very much for clearing. Thank you.
Okay.
Because
So actually, we are running out of time. We have I've already planned a session for the programming part. So do you have any
Thank you,
other
sir.
doubts or any other questions?
Yes, sir. The last part, the last video, kernel PCA, that compressed representation, that part is a complete bouncer to me, sir.
Compressed representation for week 2 you are talking about?
Week 2, yeah, 2.5, lecture 2.5, kernel PCA.
So step 3, sir.
Okay, so
Modified step 3. I mean,
Yeah, modified
correct.
step 3 to be precise. I mean, what is the problem with the step 3 and then the modified step 3? Like, what are we doing? Basically, we are not
modified
calculating.
step means you are talking about the centering of a kernel, is it?
No. Before that.
Okay, so I have to go to the lecture, go to the slide will do the work for me.
Yeah, sir. I mean, if you
Yes, sir.
recall, if that should be fine. I mean, either ways, it's fine. See, basically, what he said, I think, if I understood it right, we won't calculate the principal component. We will just
Okay, I got the
kind of
point where you got it.
we'll just
Okay.
store the projected data, and then we'll use that for downstream tasks and things like that, right? So
Yeah,
essentially, there's no reconstruction of the data back here.
Yeah, okay, I got your point where you let me open my slides here, then I'll able to explain.
And second related to this is I'm not just to the sir you, but to everybody. Like this notation is, I'm now, it's like getting over my head because I'm not able to visualize alpha kj and things like that. Should we take some data, basic data, and do it and see it? Because it's all in the air for me, at least the kernel PCA part. Is there a way to kind of take some basic data? Do you have some data which you can give us, 2, 3, 4 data points which we can use for this, or should we generate it ourselves?
Okay, so if you want to do such calculations by hand, then I don't think it makes sense to do calculations, but
No, even if we use, let's say, NumPy but how does that matrix look like? What is alpha kj?
So
Then is height row vector, how does it look
exactly, sir.
like? It's
We
just
just want the
very,
visual
yeah,
representation of alpha
uncomfortable.
and kij like that, sir. So that will be great.
Like, how does it look like? I'm struggling with that. Till there, it's fine. Till there, I've
Yes,
understood
sir.
most of it, but just this part is a bit of a struggle.
okay, so visual representation of alpha or eigenvectors, so that is not easy task to visualize those eigenvectors, and so these are just vectors, right? And if you draw your
Sorry, sir. Let me just clarify. By visualization, I don't mean geometric visualization. I mean, I want to see how the matrix will look like, how are the so that part, just that part.
Okay, so that's why I even can explain here over this thing, but
So if you solve the programming assignment, will that help us? Because while solving
Yeah.
week 1, at least I got some clarity about what Vasu is saying. So even week
yeah, of
2, I
course,
did most of them, but some of them I'm not able to understand. So
yeah, of
if you,
course,
I think
solving
if you
programming
solve,
assignment will give you more clarity of the fundamental
Okay, then
concept.
then just for this particular, I think PCA is the most difficult uh, of many of the subjects coming forward. Sir, we'll try all the programming assignments. If it's not still very clear with how this is actually flowing from one step to other, please be open to one clarification lecture later, sir. Just for this.
Yes, sure. Because week 3 also I will be part of taking that session. So if you have any doubts regarding that week 2, on you can ask on week 3 as well. Okay.
Yeah,
So,
week
or
three
even
is,
if not clear in this session or any other session, then we can have some extra session as well.
Could you please share today's slides? They made a lot of things clear for me.
Which slides? I didn't use any slides. I just
I mean,
wrote
your
out.
whiteboard. Your whiteboard. Please do share those notes.
So this is just rough work. I
That's
even I
okay. That
cannot
rough
understand
work
it.
is so useful for me to get clarity. It made sense for me.
I can share, but it's kind of rough work. I don't.
It doesn't matter. It made sense.
Okay, I will.
Please, thank you.
One suggestion for Vasu, there is one YouTube, it is a PCA based tag quest. There is not matrix, but it is pictorially or visually you can
yeah, I've seen that. See,
for dimension transformation.
I've seen that. I really liked it. Thank you for that. It's very good. I've just stuck with this kernel transformation and that compressed representation.
Yeah, that is not a good.
The modified step 3.
Okay, so let me open that.
Uma, can you place the video link here, the PCA based transformation that you're referring to?
Yeah.
That's actually a good video, statling.
Yeah, to visualize the higher transformation,
Yeah.
that is only for that purpose, and also some of the kernel things. Yeah, yeah.
Okay. Stat cuts we are talking about.
Yeah.
Stat cuts video you are talking about.
Yeah,
you had shared.
Yes, stat quest.
Yeah. They have some good explanations of each and every algorithm.
But they don't get into mathematical
Yeah, they don't
explanation the
get
way
into
we are
much of the
doing.
mathematics part, but how algorithm works, the steps of algorithm you get
At
clear
a
idea.
very broader level, that's good. At a very broader level, that's good. You will get a brief idea about algorithm and all. But since the uniqueness of this course is the mathematical derivation, so that kind of video, YouTube link we are not getting. So I think that's why we all are requesting for hands-on solving of examples and all those things.
So what Arun sir has done here is more about the mathematical aspects, statistical aspects of each and every algorithm. So that's how MLT is actually taught in any institution. If you talk about any institution, if you talk about any courses, that's how it is being taught. MLT course. It's not just go through the steps and done. He should be able to know the mathematical aspect as well and the statistical approach as well for those algorithms. So that's the idea of whole course here. But yeah, definitely there may be thousands of hundreds of resources where you can get the better understanding of the algorithm, what's actually happening in the stepwise, right? So StatSquares is one of those resources. It doesn't get into the more of the mathematical rigor part of those, but yeah, it gets the idea of what actually happening in any algorithm, machine learning algorithm. Okay. So yeah, so let me share my screen for that particular lecture slide so that I can know where. Okay, so can you see the screen?
No, not yet. Something's coming up. Yes.
Yeah, so lecture slide. Yeah, this was right. So where did you get the problem? Which step you were talking about?
Vasu.
In the kernel PC, right? Am I audible?
Yes, you are.
Okay, so
Vasu
this is
is
step
on
we are
mute.
talking about, right?
Yes, I think this was it. That's what he was talking about. The step 3.
Is he still here or left?
He's on mute. Maybe connection issue or something.
Okay. So
Sorry. I was on mute. Yeah, just if you can.
This was the step, right? That
I can't see, sir, your screen.
yeah. Just let me. Yeah, this is step.
Yes.
Okay. So let me open whiteboard, then I will explain it. Not hard one. Okay.
Modified is to skip the phi of x. Is that correct?
Yeah, skip phi of x. That is correct.
That
Let
is
me
why we are
explain this.
modifying without phi of x, right?
So while you are opening the one question, probably somebody asked. So when I do this, when I want to explore, let's say, polynomial relationships, okay. So only when I know that it's okay. Okay. How do I choose polynomial, or how do I choose quadratic versus, let's say, quintic relationship or whatever? So it depends on how the data is kind of related to each other. Okay. Okay. Got it.
How do we put in?
Your voice is from my side or even?
And he just, I think, mentioned
Yeah,
that
I got it. I
that's
got
what
it.
he was looking for.
So how do we choose the piece? Is in further weeks? It depends on classifier, things like that.
No.
Okay, so choosing P actually will get better when you will go to the MLP
Yeah.
course, right?
Okay.
So it's not just about one parameter P here. If you go to the different algorithm, ML algorithm, there are different parameters you ahead of the time you don't know what it should be. Like if you've gone through regression part, right? If you have gone through regression somewhere else, I mean MLF or something. So there we do some regularization, right? Polynomial degree transformation again there. So we never know what this parameter is. And for different algorithm, there are many parameters and we call them hyperparameter that we ahead of the time we don't know what it should be. And model itself doesn't learn those values. So I'm using some terminology here, but yeah, that should be clear in the when you will go through the MLT and MLP courses. Okay. So it's not these parameters, the degree here that we come across. So these are the parameters we never know what it should be and what the actual value of this. Even we don't know what kernel will suit for our data set, right?
Yeah.
Yeah, even we don't know if the polynomial will work fine or the Gaussian will work fine or any other kernel will work fine for our data set. It's all those we have to work around different. We have to play around those parameters, different values for parameters, and then we'll check which is giving me the best idea, best I mean the best error or whatever that you call it, right?
Okay.
Okay, so it's not nobody knows ahead of the time what it should be. Okay. So you will get better idea when you will get into MLP and where you will do some and you will apply some algorithm over the real world data set where you never know which model, even you ahead of the time you never know which model will suit for my data set and should be even apply PC or I should not apply my PC or data set at all. Okay, so such kind of things, it's like we have to play around different combinations and then we'll stick to the best parameters. Okay, so all these things are will be done will be clear when you will do all these ML courses and do some project on real world data set and all. Okay, so come to that part where you were asking me to explain that the step where we have skipped 5, right? So now what we have till now, we have PC1, okay, right? So what we let's call WK be the kth principal component, right? So it is x alpha k, right? And alpha k we have already calculated.
Alpha k.
So let me explain it now. So we have started with that we have called the principal component to be the linear combination of data points, right? That's where we have start, and we call them f phi x into alpha k, right?
Yeah, alpha k we have, beta k by n.
Yeah. So once we have alpha k, my principal component becomes phi x into alpha k because it's a linear combination of the data point, right? So these are my data points, and these are the coefficients that we have already calculated using those algorithms. Now, what will be the projection of the let's call?
But here when you're saying alpha k, it's to do with the k matrix, which has to do with the transform data, right?
Yeah. So that we have calculated using that algorithm. We find k matrix, then we find eigenvalues, eigenvectors.
Yeah. But k here is the piece kernel k.
No. K here is the kth index. Oh, okay. Let me use some different index.
No. I'm saying this lambda, this alpha k is based on the eigenvectors and eigenvalues of the matrix k, which is the kernel matrix.
Yeah. So let me use some different index. Let's call ijth jth principal component as linear combination of the data points, and this will be alpha j. So that will be the jth, right? Jth eigenvector. Jth means the eigenvector corresponding to jth highest eigenvalues, right? And do the normalization as well, right?
Yeah.
Like root over alpha j. So this is my jth eigenvector. Okay. So this is how I define my jth principal component, right? Now, so the point was to calculate jth principal component, we need to know the phi, right? If we don't know the phi, we cannot find the jth principal component. Okay, and the whole idea of doing kernel trick is to avoid using this phi.
Yeah.
That is why we don't go to the find the actual directions, actual principal component directions. What we actually can do, we can project our data set. Let's call the ith data point xi. If we want to project into jth principal component, what will be the projection?
Can you repeat this part again once again, please?
So I want to. I don't know what is the jth principal direction, right?
Correct.
But if I want to project my ith data point into the jth principal component, what will be that projection?
Xi transpose, whatever, 5 Xi transpose.
Xi transpose into Wj, right?
Into Wj, correct.
Okay, and this will be Xi transpose, and what is Wj? This is phi x, right? Alpha j, right?
Yeah.
This thing, right?
Correct.
Which one is I? Which one is j? Okay.
Okay, so here my data points actually become phi xi, right? Because I have already transposed.
Yeah, that's what I'm saying. 5 xi.
So this becomes phi xi transpose, phi xi transpose, phi xj, right? For this, it's actually not functioning well. My whiteboard is not functioning well due to some reason. So this becomes, so if you do some calculation here, it actually nothing but summation over, because this actually comes from the k, right? K.
Okay.
Okay, xi into xj, and you have to sum over j. And this becomes okay. So here it becomes alpha j, right? So that's how you calculate. And even now we don't need phi at all for the finding the projection. So this becomes your projection of the ith data point on the jth principal component. So projection of. So how you just remember this terminology? If you have to find the projection of the ith data point on jth principal component, it will be sum over k xi xj, and you have to run over j 1 to n alpha ij. Alpha ij is what? Alpha ij is just alpha is for ith data point, it will become alpha I. This will become alpha I1 up to alpha in, right? So alpha ij you have to take from this matrix.
I got the essence of it. We are not calculating WK anymore. We're direct or whatever W anymore. We are directly calculating the projection towards the kernel matrix, dot products from the kernel matrix. That yeah, got it roughly. But I'll do that. I'll take some data and kind of run through the whole calculations, not by hand, but just how the whole thing is flowing, and then I'll understand what is this I, K, J. Which way are we moving row wise? Which way are we moving column wise? I'll do the programming assignment maybe after that.
Okay, sure.
Thank you.
One silly doubt maybe. It was alpha j before. Suddenly, how it became alpha ij? I'm suddenly getting that point.
Okay, so here, if you look at this steps, I just skip some step here because I have to do some all the calculation here.
Okay, fine. Yeah. Then.
So this thing, what whenever I wrote all is this stuff, but here this thing. So here I wrote 5 xi transpose, right? And here I wrote 5x into alpha j, right?
Yeah, no, I got that. Up to that we are transforming k, but there it was alpha j only, right? Suddenly.
Yeah, alpha j. So actually this you can write it as this thing, you can write it as this particular thing. This will become, so what is so this you can write.
Yeah, the down. I understood that. All summation of k xi xj.
Summation over 5 xj, and this become alpha ij, because this alpha alpha
Okay.
alpha
There.
j is a vector, right? This vector.
Okay. Yeah.
So this become alpha 1j, alpha 2j, and alpha nj. This thing.
Yeah. Okay.
This is your this is your phi x1, phi x2, all these points, and this multiplication. So
Okay.
that I wrote as a summation thing, this summation thing.
Right.
And then you have to do with ij. So this particular thing will become k x I xj, and this become alpha ij.
Okay. It's like too many notations, really confusing for us here.
Notation, just if you know what vectors mean and what are those elements and what actually happening, what operation we are applying, then all the operations will be
Yeah.
clear.
We are just convey where the vector is coming and where the scalar. That is where it is
You have
confusing.
to keep all these things in mind, right? Where we started. Remember, alpha j we have started with calling it the coefficient of that linear combination, right?
Okay. Yeah.
Okay.
So that part of combination is combination of linear combination is already mentioned in the videos.
Yeah. It's in starting. Only it is mentioned that.
Okay. Okay.
Sir, one thing,
Hmm.
which book actually you recommend for this topic, sir? Kernel PCA. If you want to refer some notebook, textbook, sir. So can you please suggest some names, sir? I can see a couple of names over there, but I'm not able to identify which one is actually applicable for this particular topic, sir.
Okay, so for myself, I just refer to the video lectures. That's it. I didn't refer to any other references for kernel PCA. For me, that lecture itself was sufficient to understand what's actually happening, and I didn't actually refer to any resources. If I come to know any resources, I will post it on this course. Otherwise,
Yeah, please, sir. Yeah, thanks, sir.
this point of time, I don't know any other reference for the kernel PCA. I'll try to find it out. Okay.
Sure, sure. No worry. Thank you, sir.
Wasn't the lecture itself sufficient for understanding this concept? Have you gone through the concept lecture?
Yes, sir. I have already gone through
Yes, sir.
all the lectures.
The last one multiple times.
Yeah, yeah, multiple times, sir. But just for like visualization purpose, sir, we just wanted to
I'll do
know
it, Hari.
if the video.
I'll try and do it next week, and I'll
Thank you.
try and share.
Thank you, sir.
I'm sure I'll get stuck somewhere, and we can like help each other.
Yeah, thank you, sir.
Sir, any book recommendation for complete machine learning?
So okay, so uh, I actually referred to understand the concept. One is the Bishop book, right? That is already provided on the portal, I think. And one is ESL, Elements of Statistical Learning, which is more mathematical. So if you understand the concept, then to understand the actual mathematical concepts and all, you can follow that ESL book. Elements of Statistical Learning. It's very famous for machine learning courses.
Yeah, very famous actually.
Yeah.
And
And
what is the first one? What you said?
the Christopher Bishop book.
Okay, okay, that pattern recognition.
Pattern recognition. Yeah. That.
Any edition of that book? Because the edition is available of 2004 or something like that. So.
Okay. So their concept was very easy to understand.
Mm-hmm.
So you can refer to that book to understand different ML algorithms. Okay. Okay. So there are many books.
Pattern recognition and machine learning, right, sir? That's the book.
Pattern recognition and machine. Yes, I think yes.
Yeah,
if you write Christopher Bishop, you will get that book.
Yeah, yes, that one only, Basu. That one only.
I think it's on the course introduction page also. Let me just.
Yes, that one only.
Okay. So should we go to the programming part now because it's already 7:15?
Yes, sir.
Okay, so it will take longer time to. So how many of you have solved the programming assignment?
So I couldn't solve the last part of week 2. Last question.
Okay. Okay, give me 5 minutes. I will be back and then to start the programming assignment. Not 5 minutes, just 2 or 3 minutes. Okay, so let's start with the programming questions.
You seem to be saying something, but we can't hear.
No, that
Please, no.
can you see the programming questions? The Colab file.
Yes.
Okay, so it's visible, right? Font size is okay. Okay, so whatever we have done in the kernel PC, we'll try to implement using the NumPy library. So here I have imported both the things, NumPy as MP and matplotlib library as PLT. Okay, so Karthik has already taken one session on the NumPy of basics, so that will be very helpful. If you haven't gone through that that session, please once go to that session. And if you're not comfortable with the NumPy library, please go to learn some basics of NumPy and try to implement using 4 different assignments. Okay, so okay, so so in this particular assignment, we will implement a kernel PCA, and we already know the concept of kernel PCA, so we'll apply using NumPy. So first, I've taken one very toy data set here. Here I've taken X as a data matrix of the shape n cross D. Remember in the lecture we have taken the convention of D cross n matrix, but for here we have taken the convention of n cross D matrix. Okay, so you should be able to do it both way around. I mean, if you have been given n by D matrix, then you should be able to do that as well, right? So if you're not comfortable right now, you can just take the transpose of X here, and the shape of X will become D cross n, and then you can apply your concept. But here I've taken the convention of n cross D matrix. It means there each and every row is an example, and each column represents the features value for different examples, right? So we have taken the toy data set. I created the circles. Actually, if you just plot those data sets using the matplotlib, I just plot the scatter plot here, right? So what a scatter plot do? If I just write the code here, so plt.scatter, it actually plot the scatter plot between two variables. So first on the x-axis I want the x feature, and the y-axis I want the second feature, right? So first feature is coming from the x matrix, right? So if I take x matrix and the first feature value, what is the first feature value? The row or column? First column will give me the first feature value, because here my matrix is n cross D matrix. Each row will represent one example, and each column will give me the first feature value. First column will give me the first feature value. Second column will give me the second feature value, right?
Yeah.
Or just give me the shape of x here. So x dot shape will give me Okay, so x dot shape will give me the shape of x. So 1000 example are there and they are lying along the rows and two columns are there. So two columns represent the features value, right? So the first column represent the first feature values for all examples, 1000 examples, and the second column represent the second feature value for all those 1000 examples, right? So for data set, I want on the x-axis, I want the first feature. So what is the first feature values? They lie along the columns, right? On the on the y-axis, what I want the second feature. So how can take it as the second column, right? That is correct, right? If I draw those, they are coming from the circle, right? That's how I draw. I created my data set. I create some circles using some 1000 examples, and I just add some noise on this data set. Okay, so that this part you can ignore. You will come to know when you will learn about the sklearn library, right?
So 0 means first feature and 1 means second feature.
The first 0 means the first column of the matrix X, right?
Yes.
If I just write X here, so what it will give me X0, what it will give me?
0th column.
0th row.
0th.
Right? But if I take all the rows with the 0th column, it will give me the 0th column. So all these are my first feature values for 1000 examples. So this particular value here, this particular value is the first feature value for the first example. This is the second feature value for the second example. Sorry, first feature value. This is the first feature value for the third example. And if I take just x0, it will give me the first row. And what is the first row? The first example. So this is my first example, two-dimensional data point. This is my first feature value. This is my second feature value for that first example, right? Because I have taken x as n cross d. If I taken as d cross n, then first column become my example. Is that clear?
Yes.
Okay. So that's all I want. I want.
What are different parameters which we are passing? Like n samples means sample size, that is 1000. And what about others like 0.9
Okay,
and
so
then 0?
this is about the noise. Because if I just don't add any noise here, I don't want to do because just I get different data set. If I don't do noise, then all data point will lie on its circle, right?
No, so
Here,
whether we are going to learn sklearn down the line in MLP or
yeah, in the MLP course.
so all these things will be explained, huh?
Yeah, obviously, because MLP course is all about implementing algorithm over sklearn.
Using sklearn.
sklearn, yeah.
So other library like Panda, NumPy will not be taught over there, sir?
It won't be taught, but it will be used somewhere. I mean, not extensively, but some basics of pandas and NumPy will be helpful in ML.
Matplotlib, C1 and all. Okay.
Yeah, all these will be helpful in MLP as well and MLT as well. In MLT, we won't be using pandas, but we will be using NumPy only. NumPy and Matplotlib.
Matplotlib and NumPy. Okay.
Okay, so that's how your data set is distributed. Now we want to apply my kernel PCA over this data set, right? Because if I apply the PCA here, it won't work fine because its relationship is not linear at all. Because I can easily visualize because there are only two features. If had more than two features, then I cannot even visualize how the data set is distributed. So I will be applying kernel PCA over this data set, right? Till this point, any doubt? Okay, so this was my first question. That should be okay. Second, okay, so how many examples, how many samples that I just actually can get from the x dot shape? Right. The next question is you have to find the kernel matrix K using the polynomial kernel with degree 2. Okay, so what is the polynomial K matrix when we apply the polynomial kernel? Okay, so first I will write the code for the polynomial kernel. Let me write that once. So let's call it polynomial kernel. Call it polynomial kernel, and it takes the parameter x and the degree, right? P. Okay. So remember in polynomial kernel we do x transpose x, right? So what it should return? It should return x transpose x or x transpose. What is should written x transpose or x transpose x?
X transpose X.
X transpose.
X transpose, because remember I take the convention of n cross d matrix here,
Okay. Sorry.
right?
Okay. Yeah.
That's why I
Okay.
was asking this question.
Yeah.
Don't be
Okay.
confused within this convention. Okay, so
Yeah.
where is that count? So this will become my x transpose x. So sorry, x transpose. This will become x into x transpose. And remember the polynomial kernel function. It's x transpose plus 1 raised to power p. So plus 1 raised to power p and raised to power p. So this operator at the rate is actually doing matrix multiplication of these two matrices. And remember, in the matrix multiplication, you can do this operation plus 1 or any operation you can apply on the NumPy arrays. And then you can even raise to power those p. So raise to power p will what it will do? It will raise to power for each and every element of that matrix. Okay. So I want you to figure out the difference between these two operations. One is delta, one is there are three operations. I want you to figure it out. One is called numpy.matmul. Another is that at the rate operator, and another is numpy.dot. Okay, so it looks like a dot some matrix p. Okay, so please go and actually figure it out what these three functions do for doing the matrix multiplication.
Actually, there is a, for the last one, there is a, I think there is a better representation, but a cleaner. It's np dot bracket a comma b.
np dot?
np dot.
Yeah.
Write down, sir. np. Just if you can write down. Last one. np dot. Again dot. dot.
Dot.
Bracket a comma b.
Okay, so that is same as this a dot.
Yeah. So that's the same. The both are the same. It's just a clean. Last one is a little cleaner. Like, you know, you're taking two matrices.
That is fine. That depends how you use it. I generally actually follow this operator till at the rate. Okay, so I just want you to figure it out. All these operator, how they work. Okay, so they all use for the matrix multiplication.
Sir, one query over here. In this case, polynomial kernel, don't we have to centralize the data set?
Okay, so
Before?
what kernel PC algorithm says, first you find K matrix and then you center K matrix, right?
Okay, I did it. I did it earlier as well. Okay, right.
Okay, so I'm not writing it again because I've already wrote the solution here. Okay, so I wrote the polykernel function here. What it is doing, it is taking the matrix, data matrix, and applying the polynomial kernel, and it will returning me what? It returns me the K matrix, right? This is my K matrix. Is that clear?
Yeah.
Okay, and what was my actual question? Question was, you have to find the K matrix and then you have to do this operation. Just take square of every element, sum over all those elements, and then do square root and do 1 by n. So for that, it's easy part. Do square of every element, do the square of every element, then do the square root of every element. Then do the sum of every element, then do the square root and divide it by n, right? So it will give me 2.096. Then, okay, so next is you have to apply the Gaussian kernel here. Okay, so I've done here polynomial kernel of degree 2. You can even apply degree 3, degree 4, whatever. Just change the value of p, and you can find the kernel matrix for every such kernel functions. Okay, similarly, I've done for the Gaussian kernel. So how you define the Gaussian kernel? You cannot directly do here as I did here. I did as finding the K matrix as x transpose plus 1 raised to power p. Here you have to find the Gaussian kernel function value for each data point, each pair of data point, and then you have to store into the matrix, right? So okay, so let me write it down here. So I write the function. Let's call it G kernel. Let's just call kernel like this. Make it later. it will take two data points. Let's call them data points as A and B, and I will apply the Gaussian kernel with the parameter sigma. Let's call that S. Okay. Now, so what it is, it should return. The answer is already here. Okay, let me write it. So it should be a norm of A minus B, right? Data norm of A x minus y. So it should be, so all those linear algebra functionality is present in the module np.lin else. Okay, so whatever linear algebra functionality like finding inverse, finding not transfer, finding inverse, finding norm, or solving the different linear system of linear equations, or all such linear algebra function are present in the module called np.linear. Lin dot, so norm, there is one function np dot norm. So what norm I'm to find? I'm to find A minus B, right? A minus B. Now it should be a square, right? So I will take it square. And it should be divided by 2 sigma square, right? It should be divided by 2 sigma square. Sigma is S square, right? And this whole thing is e raised to power, right? This is all raised to power, all e raised to power, all these things. So this will become np dot ex. Any doubt here? So what it is doing, it's taking 2 data points, any dimensional data point. It is finding this kernel value, right? Similarly, I wrote it here. So the same function here. Now what I am doing for finding the K matrix, I will take I will store each and every element in that matrix. So what I'm doing here, you can even read it here. So I'm just creating an array, and in this I just pass this list. What is this list? It's taking I and jth element and applying this function g kernel function. It is taking the ith element, ith data point, j data point, and sigma is already given to us. And for every such I and every such j, it is calculating and storing into this list. Now I will just reshape into n cross n matrix. Right? Is this part clear? What I'm doing here? I'm just taking each and every element and calculating the kernel function value and storing in an array. Right? Okay, if not clear, you can ask me. I can even write it down. But it should be easy part, right? It's just storing different elements, just calculating the values of kernel function from this definition and then storing into a matrix.
Sir, what is sigma again?
Sigma is just that in the kernel, remember in the RBF kernel, Gaussian kernel, the function value is e raised to power a minus norm of a minus b square upon 2 sigma square. That's parameter sigma for Gaussian kernel. And in this question, it is given parameter equal to 2.
Okay.
Okay. Now for our data matrix, kernel function, I can write x. I can pass the parameter x and the sigma value 2, and then calculate this particular value. It's just taking the square, doing some square root and divided by n, right?
So
Okay.
it will calculate for all I and j. I need not put a loop over here for
You can
calculating
even you can even put the loop over here, and I just pass the list. This list. You must have gone through how to create this list, right? In Python code.
Yeah, right. Oh yeah.
Okay. So the next part is centering the kernel. Remember centering the kernel. You have centering the kernel. You have to apply this particular expression. Sir has wrote it down in the lecture. So you have to create a matrix of all the entries as 1 by n. So I've created an array of shape n by n, and so np.1 give me a matrix of shape n by n, where each element is 1. Okay, and I'm dividing each element by n. So of this particular matrix, every element is 1 by n, right? And what is n? N is the number of example here. Okay, or in the K matrix, it is n cross n. So it doesn't matter whether you take the columns or number of rows. Okay, so it's actually number of example in our data set, and I'm creating a matrix of all entries and by 1 by n, right? So this is my matrix with all entries and by 1 by n, and this expression will give me the uh, centered key matrix. Okay, if you want to prove how it is actually doing the centering of the data set, you have to do some mathematics over those. As actually sir has given the idea how to do that, right, in the lecture. Okay, so this thing is done, centering of the kernel. Once I have the centering of kernel, what should be the next part of the algorithm? Now it's asking for finding the projection. Before finding the projection, what we have to do? You have to find the eigenvalues of center K matrix, then corresponding eigenvectors, and then the normalization of that, and then for finding the projection, you just apply that formula. Remember that formula: K xi xj and alpha ij and summation over all the j's, right? So that's for that I've written this function projection. So what I'm doing here, I'm just calculating the eigenvalues and eigenvectors for that matrix, kernel matrix, right? So I'm taking that as a parameter here, that center K matrix here. Okay, so my here is a parameter which I pass, which is actually nothing but centered kernel matrix. Okay, so I will find the eigenvalues and eigenvectors using this function called np.linearity.eigh, or even you can use EIG. Okay, both will give me the eigenvectors or eigenvalues. Okay, so it will actually, this function will give me a tuple in which the first element are the eigenvalues and the second value is the corresponding eigenvectors, and in the order itself. So eigenvalues are always increasing order in this particular function. Okay. So this is the function for calculating eigenvalues and eigenvectors. Once I have those, what is my lambda 1? The highest eigenvalue, which is I can take it from here using the last element, and the second lambda 2 will become my second largest eigenvalue. That is my second largest element of this tuple, this value. Okay, this vector. Now, what will be my alpha 1? Remember, you have to take the unit vectors, unit eigenvectors, right? So this eigenvector, whatever we are getting, we have to make sure that they are unit norm. So what I will do, I will take the eigenvector corresponding to the last or the highest eigenvalue. That will be my last eigenvector in this list, right? And I will divide it by the norm of this eigenvector to make sure that it comes into the unit norm, right? Then alpha 1 actually be normalized using square root of over eigenvalue. So I will just do the square root over eigenvalue. So this will be my
So
alpha 1.
one query. If I pass a single parameter to the norm, it will give me the length over.
If I
In this
pass
case,
the single parameter to norm, then what?
it will give me the length of that vector.
Yeah. So you can
And if I
write.
pass two parameters, it will give the difference, like the length of that.
No.
Okay,
Norm
okay.
only takes the one parameter. Like let's call one
Sometime back we took A and B now over there.
A minus B bit 2.
Okay.
Right? So if I just write it here, np dot, let's take these two parameters, np dot array is my one, let's call it 2 comma 3, one vector, right, row vector. Similarly, let's call p as np dot array, again take some row vector. Okay, so if I pass np dot else, so if I pass two parameters, if you want to pass a comma b, then it will show the error because it takes only one parameter. And if I pass a minus b, it will actually first take a difference and then will find me the norm
Again,
of
find
that.
the length. Okay. All right. Thanks.
So up to this part is clear, right? What is alpha 1? Alpha 1 is actually unit eigenvector divided by root alpha 1, right? So sorry, lambda 1. So lambda 1 is the highest eigenvalue here. I just take the corresponding eigenvector to make sure that it's unit norm. I divided it by the norm of this vector, and then the normalization by the square root of lambda 1. Right. Similarly, the second alpha 2, right? Second eigenvector, I mean the eigenvector corresponding to second highest eigenvalue. I made it the unit norm, and I have divided by the square root of the lambda 2, right? So this become my alpha 1, this become my alpha 2. Okay, so what is the projection? Remember, this is just k times m, right? So here I do this convention just to make sure that all it gives me the vector for all the data points. M is my k matrix, right? And this is my alpha vector, alpha 1. So this will give me the vector where so this will give me by n by 1 by n vector, right? So each element will be the projection of each data points on the that principal component.
Sir, one small doubt here. In the while calculating the alpha one, you just used eigenvec is to comma minus one. Isn't there should be minus one only for the
No.
last?
So actually, this here, this actually give me the eigenvector as a columns.
Okay.
Okay, so here it will give me the matrix. So last column will be my the eigenvector to the highest eigenvalue. The first column will be my first eigenvector, or say the eigenvector corresponding to the least eigenvalue. Okay, and I want the eigenvector to corresponding to the last, or say the eigenvector corresponding to the highest eigenvalue. That is my last column.
Okay, so got it. I was just confused about minus one.
Yeah, it's a good point. It's a good point. Here, rows doesn't represent eigenvector, columns represent the eigenvector. That's how this function works. The np.lineal.eigh.
Can you repeat the written projection? I'm not getting what is that M actually.
M is actually that I will pass center kernel matrix that I already calculated here, right? Center kernel matrix. So for my data set, I will pass my kernel center kernel matrix, and then I will get the projections for that. Okay, so there are two functions in np.lineal. One is eig and one is eigh. So please go and check what those functions does. These two functions do. One is np.eig, another is np.eig. So these two functions, please check it out. What is the difference between these two functions? You can use any of these here. It won't affect your answer.
Okay.
So actually, this function always accept only symmetric matrix. But in our case, K always is symmetric matrix, right? It's always n by n matrix. So it won't affect whether we use EIG or EIGH.
Excuse me, sir.
Yes.
Sir, in the calculation of alpha 1, in the division part, np dot square root of, is it not n lambda?
Okay, so give me 1 minute.
Yeah, sure.
Are the slides visible?
It's
yes,
coming
sir.
up.
Yeah.
So here, sir calculated the centered kernel matrix here, right?
Yes, sir.
Then sir calculated the eigenvalues as n lambda 1, n lambda l, right? So this n lambda 1, n lambda l are the eigenvalues of K matrix.
Okay.
Then sir take the square root of n lambda 1. So what sir did, sir take the square root of n lambda l. So sir is calling n lambda l, n lambda 1 as the eigenvalues. I'm calling lambda 1 as the eigenvalue.
Okay, got it. It's just the lambda value of, eigenvalue
Eigenvalue
of K matrix.
K matrix here.
Yeah, okay, sir, thank you.
And why sir come to n lambda? Because sir has actually initially working with C matrix, right, which is 1 by n xx transpose. And then sir called that x eigenvalues of xx transpose and x transpose x are similar. So sir takes lambda 1 as the eigenvalues of the covariance matrix. So the eigenvalues of x transpose x become n lambda 1. That's why sir has used this convention n lambda I. So don't be confused. You just find the eigenvalues of K matrix and take the square root over that K matrix. Okay.
Okay. Okay, sir. Yeah, thank you. Thank you.
Okay, so that's all about the programming assignment. You please go and do by yourself. Don't look for the answers. Don't look for the solutions. Do by yourself. And yeah, so that's all from my side for this session. If you have any other questions, you can ask.
I have a few questions on week 1.
Okay.
Essentially, when we're talking about residual,
Hmm?
it is the distance between where the original point is to where it is projected to, correct?
Okay, so there are two terms, residual and error, and
Reconstruction error.
yeah, reconstruction error.
Yeah.
I have to check. I'm not pretty sure about these two. So, but it's actually related to that projection, how it where it is projected and actual value and the difference between two. So I have to check the actual difference between these two terminologies. Right now, I'm not pretty sure about that, and better to ask on the discussion. The Karthik will be the right person to answer
I
on.
think I remember Karthik said in last that is a vector residue, and the reconstruction error is that actual value.
Norm of that,
dot
right?
product.
Yeah, square
Norm,
norm. I think norm
Yeah.
square. I think so.
Okay, okay.
Square
So
norm.
that's all we do. Convince this all about the convince about what we call as residue and what is. So it's all actually the actual value of that point, and we project. So how much error has been what kind of information we have all lost using by projecting that data point onto the principal component.
Okay, okay. That's one. And the second one is related to the step where it is written as optimization. I was just going through it once again. Karthik had already explained this, that W transpose CW is equal to lambda1 maximization for the eigenvalue. And he mentioned it as argument maximization for eigenvector. So what am I clear about what I'm saying, or
So that is for W transpose CW, right?
W transpose CW is equal to lambda1 if it is maximization of the lambda1 if it is maximization for the eigenvalue. Argmax, it is W1 is what he said. When he says argmax, argument is what it is. In this case, the argument is WT and W, or what is that?
No, I didn't get the point of argmax. R is okay. Max is okay. That will give me the eigenvalues because W transpose CW is nothing but that lambda, right?
Correct.
So that will give me the eigenvalue. So what do you mean by argmax of what?
Argmax of W, the unit vector. W, how to write it? I'm not.
See, optimization is basically what is the value of W such that W transpose CW is maximized. W